Plate tectonics. The Earth is made up of three main layers: the crust, mantle, and core. Between the crust and mantle, the cooler, brittle lithosphere floats on the hotter, semi-solid asthenosphere. The core has two distinct parts, a liquid outer core and a solid inner core. Heat within the Earth comes from two main sources: residual heat and radioactive decay. Residual heat is a gravitational energy left over from the formation of the Earth. Radioactive elements decay over time and produce energetic, fast-moving decay products, particles that collide with atoms and molecules in surrounding rocks and give up their energy as heat. Deep inside Earth, all this heat energy softens rocks to the point that they can flow. The mobile rock asthenosphere beneath the rigid plates lithosphere is believed to be moving in a circular manner, somewhat like water when heated to boiling. The heated rock rises to the surface, spreads and begins to cool, then sinks back down where it is reheated and rises again. This cycle is repeated over and over to generate what scientists call a convection cell or convective flow. The theory of continental drift was introduced by Alfred Wegener in 1912. He contended that around 200 million years ago, the supercontinent Pangaea began to split apart. The diagrams on this slide show the breakup of the supercontinent Pangaea. At the time Wegener introduced his theory, the scientific community firmly believed the continents and oceans to be permanent features on the Earth's surface. Wegener devoted the rest of his life to doggedly pursuing additional evidence to defend his theory. After Wegener's death, new evidence from ocean floor exploration and other studies rekindled interest in Wegener's theory, ultimately leading to the development of the theory of plate tectonics. The theory of plate tectonics states that the Earth's outermost layer is fragmented into plates that are moving relative to one another. In geologic terms, a plate is a large, rigid slab of rock composed of the continents and oceans. The Pacific and Antarctic plates are the largest. Tectonic plates probably developed very early in the Earth's history and have been drifting about on the surface ever since, like slow-moving bumper cars, repeatedly clustering together and then separating. Evidence used to support the theory of plate tectonics over time have included the Mid-Atlantic Ridge and topographic profiles of ocean floors taken by sonar, paleomagnetism, mapping magnetite in ocean floor lava flows, radiometric data, classifying rocks by age, and radioastronomy, taking seafloor spreading measurements. Sonar technology first allowed researchers to map the contours of Earth's ocean floors in the years following World War II. Oceanographers discovered remarkable steep-walled canyons and lofty mountains, indicating that the seafloor is as dynamic and changing as the continents themselves. The longest mountain range on Earth, for example, is in the middle of the Atlantic Ocean and is called the Mid-Atlantic Ridge. The Mid-Atlantic Ridge stretches from Iceland in the North Atlantic to the South Sandwich Islands in the South Atlantic. Through the use of sonar, scientists also located deep fissures in the ocean bottom named trenches. These ridges and trenches are sites of continuous geological activity, including numerous earthquakes, volcanoes, and lava flows. The mid-ocean ridge, shown in red on this slide, winds its way between the continents, much like the seam on a baseball. Lava flows provide a second piece of evidence for the theory of continental drift. When lava flows out of a fissure, it contains small crystals of natural iron oxides, including the naturally magnetic mineral magnetite. These bits of iron ore act as tiny magnets, and because the rock is still in a fluid state, their magnetic dipoles are free to turn around and align themselves in a north-south direction parallel to the Earth's magnetic field. Think of these mineral grains as small compass needles embedded in the fluid rock. Once the rock hardens, however, the bits of magnetite are frozen in place. They can no longer move. Thus, the volcanic rock carries within it a memory of where the magnetic North Pole was when the rock solidified. If we examine the tiny compass needles, we can tell whether the Earth's magnetic field was oriented as it is today, or whether it was reversed. The study of paleomagnetism and the magnetic reversals of rocks supports continental drift. The conclusions from the paleomagnetic data were reinforced by the third piece of evidence for the theory of continental drift, studies of the age of volcanic rocks in the oceanic crust. Volcanic rocks contain radioactive isotopes that can be used to measure how long ago they erupted. Rocks near the mid-Atlantic ridge have been found to be quite young. Rocks collected successively farther away from the mid-Atlantic ridge have been proven to be successively older. The data on the topography of ocean floors and the magnetic properties and ages of its rocks suggest to many scientists that the seafloor was spreading. The fourth piece of evidence for the theory of continental drift was provided by radio astronomers. These scientists measured the crests of radio waves from distant quasars to get very accurate measurements of the distance between their radio telescopes. By repeating these experiments over a period of years, they were able to measure exactly the separation of the continents. Their work shows, for example, that North America is separating from Europe at the rate of about 5 centimeters or 2 inches a year. So to recap, the evidence used to support the theory of continental drift over time have included the mid-Atlantic ridge and topographic profiles of ocean floors taken by sonar, paleomagnetism or mapping magnetite in ocean floor lava flows, radiometric data classifying rocks by age, and radioastronomy by taking seafloor spreading measurements. Where the tectonic plates meet, we have boundaries. The boundaries between Earth's tectonic plates are active sites that determine much of the geological character of the Earth's surface. On this slide is an artist's cross-section illustrating the main types of plate boundaries. There are 3 types of plate boundaries. Divergent boundaries, where new crust is generated as the plates pull away from each other. Convergent boundaries, where crust is destroyed as one plate dives under another. And transform boundaries, where crust is neither produced nor destroyed as the plates slide horizontally past each other. At divergent plate boundaries, the motion of the magma pushes the 2 adjoining plates farther and farther away from each other, and any continents that might be located on other portions of those plates are pushed apart as well. Perhaps the best known of the divergent boundaries is the mid-Atlantic ridge. The volcanic country of Iceland straddles the mid-Atlantic ridge. The newly erupted molten material cools to rock and becomes new plate material. As the brittle tectonic plates crack and separate, shallow earthquakes of relatively low energy occur. This mechanism drives the seafloor spreading. So, divergent plate boundaries are associated with seafloor spreading, formation of new crust, volcanic action, and shallow, low-energy earthquakes. Because Earth is not getting any larger, if new material pushes tectonic plates apart at places such as the divergent plate boundaries, then old plate material must be pushed together and taken into Earth's interior somewhere else. A place where 2 plates are coming together is called a convergent plate boundary. The type of convergence, called by some a very slow collision, depends on the kind of lithosphere involved. Convergence can occur between an oceanic and a largely continental plate, or between 2 largely oceanic plates, or between 2 largely continental plates. At most convergent plate boundaries, one plate sinks beneath another to form a subduction zone. The plate that is subducted or taken beneath in this way sinks down to rejoin the mantle material from which it came. The ring of fire, which borders much of the Pacific Ocean, is caused by plate subduction. If no continents are on the leading edge of either of the 2 converging plates, the result will be a deep ocean trench. The Marianas Trench, for example, marks where the fast-moving Pacific plate converges against the slower-moving Philippine plate. The Challenger Deep at the southern end of the Marianas Trench plunges deeper into the Earth's interior, nearly 11,000 meters, than Mount Everest, the world's tallest mountain, rises above sea level, about 8,854 meters. A very different situation occurs if continents ride on top of both converging plates. They will collide. Continental material will be compressed together like crumpled cloth and pushed up to form a high, jagged mountain chain. The Himalayan mountains are an example of a continental convergent plate boundary. If a continent rests at the leading edge of only one of the 2 colliding plates, the denser oceanic plate will subduct beneath the continent. A deep trench may form a short distance offshore, and the continental material may be crumpled into a coastal mountain range. In addition, the subducting tectonic slab may partially melt, and thus provide magma that rises to form a chain of volcanic mountains parallel to the coast. The third kind of boundary between plates occurs when one plate scrapes past the other, with no new plate material being produced. The San Andreas Fault is the only currently active plate boundary within the continental United States and is an excellent example of a transform plate boundary. The process by which two plates slide past each other is not smooth. Over time, the motion of plates compresses and strains rocks at the boundary. Friction normally prevents the stressed rocks from moving, but periodically the rocks simply break, moving as much as several meters in one sudden burst. When they do so, an earthquake occurs. An earthquake is described as an abrupt release of energy. No mountain building or volcanism is associated with transform boundaries. However, earthquakes are known to occur at all three types of tectonic plate boundaries: divergent, convergent, and transform. Let's talk about earthquakes next. Seismology studies the waves of movement in the crust of the earth. The basic idea of seismology is simple. When an earthquake occurs, waves of vibrational energy move out through the rocks. This movement is called a seismic wave. Some of these waves travel deep through Earth's center, others move along the surface, and still others bounce off layers deep within the planet. Seismographs can measure the movement that emanates from an earthquake. There are two classifications of seismic waves following earthquakes: compressional or longitudinal, and shear or transverse. Compressional or longitudinal waves are like sound. The molecules in the rock move back and forth in the same direction as the wave. Shear waves, on the other hand, are transverse waves like water waves in which the molecules move up and down perpendicular to the direction of wave motion. Shear or transverse waves cannot pass through liquid substances. Mapping the locations of waves transmitted following an earthquake allows for determining the layers of the earth, as well as the epicenter of an earthquake. A scale for measuring the intensity of earthquakes was invented by Charles Richter. The seismograph is the oldest technological development related to studying plate tectonics we've discussed in this presentation. Its invention can be traced all the way back to 132 AD. In comparison, sonar had its origins post-World War II in the late 1940s, paleomagnetism in the 1950s and 60s, and radio astronomy in the late 1980s. The newest technological development related to studying plate tectonics is seismic tomography. As more and more seismic data are collected and ever faster computers permit new ways to process those data, a new branch of earth science called seismic tomography is enabling geophysicists to obtain astonishing three-dimensional pictures of Earth's deep interior, including deep regions of different rock types and magma. We are now able to document the basic movements of cold subducting slabs, hot upwelling mantle plumes, and the convection cells that characterize plate tectonics. A seismic tomograph provides a picture of Earth's deep interior based on millions of individual measurements of seismic wave velocities. This image reveals hot rocks, red, around the Pacific Ocean rim, and cooler rocks, blue, under the continents.